Hi everyone, sorry, I'm just doing a little bit of running around this evening, trying to get everything organised. I can't work out to put my computer without ending up with a big bright light over my head. Maybe if I move back a little bit, I don't know. We'll sort it all out later on. It looks terrible, I think you'll agree. Okay, so I know that it's chemistry tomorrow morning. We'll take my glasses off as well so they don't shine. I know it's chemistry tomorrow morning, but I'm not available tomorrow evening, so I thought we'd get started tonight, really, so that you can watch this tomorrow after your chemistry exam if you want. Hi guys, good to see you with us tonight. And just do a little bit of physics. If you have any specific questions, I will try and deal with those, of course. So just, yeah, shout up if there's anything in particular that you want me to have a look at, and I will do my best. I've got 4 or 5 things. We'll look at doing about 20, 25 minutes and take it from there. If there's anything you think I'm missing, yeah, get involved. So I've done some of my very best drawing skills because I thought the first place we could start, we'd start somewhere nice, relatively straightforward. We could start talking about the national grid. Hi Morgan, do love coming to join in and the GCSE, don't you? So I'm going to tilt this down a bit because I think you're less bothered about me and more about what I have on offer for you today. Okay, so this is my incredible diagram of the national grid. I'm sure you'll enjoy looking at it. So what we've got here is we've got power stations at this end, and then we've got this transformer here in between the power stations and the transmission lines in the middle. And the job of this transformer is to increase the voltage. So here you're talking maybe 25,000 volts. And then by the time it goes through this transformer here, the voltage has gone up maybe to 500,000. And then we've got the transmission lines. Now, these are the power lines that you've probably seen out and about. They run up through the mountains. And then it comes down off the transmission lines through a step-down transformer. So you should be able to spot which one's which, because this one's going up onto the lines, and this one's coming down off the lines. And the job of this one is to reduce the voltage, because high voltages are dangerous in the home, where you don't really want more than about 230 in your home in order to keep the electricity that you're using safe. And there's another reason as well. So as the voltage goes up onto the line, so as you go from 25,000 to, yes, there are those green boxes, yeah. So this transformer here, as the voltage goes up, the current goes down, so they're opposites to each other. And if you reduce the current in an electric wire, you reduce the resistance. And if you reduce the resistance, you reduce the amount of energy lost. So the important idea here is that we will lose less energy in the transmission lines. But as they come down off the lines, that high voltage is, 1, dangerous, and 2, is not very useful because there's not much current to actually do the work that we want it to. So we need it to be a higher current and a much lower voltage for safety. Okay. Now, consumers. I have seen exam questions in the past where they ask you to name a consumer. So just think about someone who uses electricity. You are users, so homes, schools, hospitals, factories, offices, anything that uses electricity at this end works really well. If we've got the national grid, okay, so if we use our diagram, these power stations can be very different. I've drawn an absolutely fantastic picture of a coal power station. I think inspired this one. But these days, there's a huge variety of ways we generate our electricity. So that's deliberate. The national grid wants what we call diversity of supply. And it's where there's lots of different ways of generating electricity, because if, say, the wind turbines off Coleman Bay, if they aren't particularly effective because it's not very windy, then everybody in the UK is going to struggle for electricity. So you want a good mix. If you've got lots of coal power stations, lots of gas power stations, nuclear power stations in the mix, wind turbines, solar panels, that builds security, because the weather, which is really variable, can cause problems in meeting all of the supply. The national grid will, if there's a fault, if there's a power cut somewhere, the national grid will turn off bits of the grid and turn on different bits, getting people reconnected as quickly as possible. They do something else as well. So they monitor the demand for electricity. So if, I mean, the classic example is what happens at the end of EastEnders. So because everybody loves watching EastEnders and they watch it live, right at the end of EastEnders, everybody goes, "Ooh, wasn't that exciting?" and gets up and heads for the kitchen. And when you're in the kitchen, you put the kettle on, maybe you make yourself a slice of toast. All of a sudden, you've got maybe 2 or 3 million people heading for the kitchen, a couple of 100,000 kettles being turned on at the same time. Your kettle uses a huge amount of electricity, so all of a sudden, the whole UK wants a whole load more. And that means that the national grid sees it coming. They're watching EastEnders, they're watching the football if it's halftime during a big game. They're watching for that sort of thing. And if they see that sort of slight pickup, then they will just turn on an extra power station or two to balance that out. Now, just while we're on that subject, because we've got 3 or 4 of these sorts of power stations in Wales, when you want fast demand for electricity, you need a power station that you can turn on and off really quickly. Nuclear power stations, for example, you're talking years to bring one of those from cold to hot. So that's no use for this. But pump storage is what it's called, or hydroelectric pump storage. And that's where you have 2 lakes. The one at the top is full of water. And as that water runs down the hill, it's got a huge amount of energy. So gravitational potential energy is turned into kinetic energy. And the turbines at the bottom of the power station, they capture that energy, turn it into electrical energy, and distribute it through the national grid. And they can go from generating almost nothing to generating quite a large amount of electricity in 5 or 6 seconds. So enough to meet the demand of you heading for the kitchen for the kettle. But they can't keep doing it for very long. So maybe they'll only run for an hour at the most. But that's okay, because most of us have then settled down watching the next episode of Game of Thrones or whatever. So they're able to meet that short-term demand. And then they do something really clever. They wait until there is a low demand for electricity and the price of electricity becomes really cheap. And they buy electricity back from the national grid and they take the water back up the hill and put it back at the top ready for the next time it's needed. So we kind of can use that to store electricity. So in the daytime, if we've got lots, we can store it in these reservoirs at the top of mountains, allowing it to come down the hill later on when we need it back, right? So just a clever thing. Heads up on that one. There's like 3 or 4 of them. There's one at Dinorwig Electric Mountain near Llanberis. There's one there. There's one at Festiniog as well. So we've got a few of them in Wales. So it's quite possible. The example, do like asking questions about things that happen in Wales. It's quite possible that we'll get a question, something to do with those things. Okay. I was going to move on from there next, unless anyone's got any questions on the national grid in particular before I move on to the next bit I was going to do. Okay. Yes, I can do, but because that's triple, I'll do that a little bit later on, if that's okay. So I'll just point this down a little bit here. So I've drawn the circuit. A couple of students asked me at some point today, which circuit symbols do we need to know? And obviously there's a big long list of them, but these are the big ones. If you know these, you can probably get your way through most physics exam papers. So battery, ammeter, bulb, voltmeter, variable resistor. This one's a bit weird. This one we can change the resistance of. You might see a resistor. A resistor doesn't have this arrow through it, and that's fixed. You can't do anything to change that. But this arrow means that we can slide. You possibly used it. It makes a terrible noise. You can slide the bit at the top, and that will allow you to change the resistance of the resistor. So in this circuit here, if I was to change this, the brightness of this bulb will get brighter or dimmer depending how I vary the resistance of this. Other circuit symbols while we're here, this is a different type of variable resistor. See how we've got the rectangle again, and this time we've got a line through it with a hockey stick on the end. This guy over here is a thermistor. And right down here, we've got something really strange. We'll talk a little bit more about it later on. This is a diode. Diodes are very a bit odd. They only allow current through one way. But we've got a diode. So it might be that they take this or this and put it in the circuit here instead of the bulb. So what could they ask you to do here? Well, it might be that they don't put the ammeter in the circuit and they ask you to draw one in. They might not put the voltmeter in and they might ask you to draw one in. They might draw absolutely nothing and leave you a blank bit of space on the page. And they might ask you maybe a 6-mark question. And they might say, draw a diagram if you want. Describe an experiment to test the resistance of a bulb. And in order to do that, we need ammeter reading, voltmeter reading. So we need a current reading and a voltage reading, potential difference. You can use both. And we need somehow to change the size of these two readings. So my variable resistor will allow me to change the current and change the voltage through the lamp. And that just means that I'll get a range of results. So I'll get something different. And that will score you all 6. So drawing the circuit correctly and saying use the ammeter to record current, the voltmeter to record voltage, and use the variable resistor to alter the current and voltage, and off you go. Okay, so there's an easy 6 if that one comes up. Don't be put off just because it's circuits. Lots of us get a little bit nervous when we see the circuit questions. We're not big fans, but don't be scared of those. They're actually relatively straightforward when they come up. You've got some equations on page 2 of your exam book. A bit like tomorrow morning, you're going to have the table of ions at the back of your chemistry. You've got equations at the front. There's nothing to do there. You don't need to fill any of those boxes in. You don't need to try and turn any of it into symbols or anything. Leave page 2 alone. Just know it's there. The big ones you're going to need for electric circuits are voltage equals current times resistance. V equals I for current, remember, given in your exam booklet on page 2. Power is current times voltage, also given in the booklet, but this one will be I again here and a big V here. Can these be put in the triangles if need be? You can turn them into triangles if you want. I mean, I can quickly do you a triangle. So if we did P equals IV, for example, so this bottom one down here, so power is current times voltage. You just write the thing and make sure you've got the times at the bottom. So yes, you can use them in triangles if you want to. There's no problem with that. The exam board won't mind. It's easy to do. Do it if you want to do it that way. Okay, so watch out for those. If you need to do that, you'll have lots of information given to you in the questions. Now, one of the biggest problems with both, well, all, not just both, with all of the science exam papers is there's lots of reading to do. And you might miss in there the important stuff. So I'd advise using the techniques that you've talked about probably in your English lessons and in other science and other subject lessons, where you skim through the text that you've been given and then you look for important things. Go and have a look for the questions, then go back. Okay, don't try and do it without using the text, because that can be really, really challenging. If you've got 2 pages like this, make sure if you've not finished the question that you read back, because sometimes right down at the bottom of the second page, you can have information needed from the beginning of the question at the front. So always keep your exam paper open. Don't fold it over on itself. Keep that information in front of you so that you can help find it. But yeah, use triangles, grab information from the text. Watch out for having to do, particularly on the higher tier, maybe on the later questions, having to do 2 things at once, where you're maybe finding the so you're doing this to find voltage, and then you're using voltage down here to find the power. Okay, there is another equation on the sheet, but we're keeping it simple tonight. Do it in 2 steps if you need to, and then use your answers as you go through. Okay, so don't be afraid to do that. That is a trickier thing to do, though, so you usually get a few more marks. Okay, some more of my beautiful drawing now. This is a voltage current graph for a non-ohmic conductor. Wow, sir, I love those. It's great. So this is a filament bulb, so like a light bulb, basically. Your light bulb is a non-ohmic conductor. It means its resistance changes. See how the line is curved? So it's like a I'm trying to think what it is. I can't do it with my hands. My hands are too straight. Okay, it's like a curve, a bit like a mountain, like a hill. And it does the same. So it's the same forward and backwards. So it doesn't matter if I reverse the voltage or the current, I still get the same shape going on. If we contrast this with an ohmic conductor, non-ohmic, ohmic, exactly the same setup. You see how this one is lovely and straight? That's telling me that there is a constant resistance. How do I know what resistance? Where's that come from? So this constant resistance is because every time I increase the voltage by, say, 1 volt, I get the same increase in current up here. So I get the same up, the same across. And resistance is the opposite of the steepness of this line. So the steeper this line gets, the lower resistance. So if we talk about this side, this one's the funny one. At first, there's a low resistance, and it gets more and more and more. So one of the great questions, the favorite questions to ask is describe the pattern, describe the trend shown on this graph. Well, you're probably going to say, as the voltage increases, the current increases. And that's great. Well done. But that's only 1 mark. And they usually give 2 for this, because they want you to say, as the voltage increases, the current increases. But, here's the second, but it increases by less each time. On this side, if we were going for 2 marks on this guy, we're going to do, if the voltage increases, the current increases by the same amount each time. So you can see how you could say the same for both. Just ignore the guy in the corner. He's supposed to be my friend, but I don't think so, really, if I'm honest. Okay, now here's my last current voltage graph. As you can see, this one looks a bit funny. It looks kind of broken, if I'm honest. So we've got the current and the voltage again. As the voltage increases, nothing happens. Nothing happens. And then all of a sudden, we get an increase. I didn't draw in the negative side, but if I had, it would look really, really boring, because if I try and make current flow the wrong way through a diode, nothing happens. If you put these things the wrong way around in an electric circuit, nothing happens. They're really useful for that, though, because you know your iPhone charger or your laptop battery charger, your television, your skybox, all of that stuff, all of your consumer electronics want direct current. They want electricity that flows in one direction. But the electricity that comes into our house through the national grid that we've just talked about, that's alternating current, which means it's going that way, then it's going that way, and then back, and then forward, and then back. So it's constantly flipping around, and it does that 50 times every second, right? So it's forwards and backwards a lot. Your laptop doesn't like that, and your phone would hate it. So instead, we use diodes very cleverly to make sure that the electricity only flows through the charger in one direction. So we can use diodes very helpfully to turn AC electricity into DC electricity. Now that's quite quick. There's more to it than that, but it's a quick use of a diode is turning AC into DC electricity. Okay, diodes. You might have come across LEDs. So the light shining above my head, making the wonderful sort of Christmas tree effect. That's an LED. LED lights are brilliant, and this comes into the domestic electricity section now. LED lights are really high efficiency, meaning they waste very little energy. One of the things I'm going to do on my last minute Thursday one is we'll look at some Sankey diagrams, and we'll talk about energy efficiency and what we can do to reduce costs and things like that. But just a mention while we're on diodes. Okay, so I thought we'd finish with a nice easy bit next. So lots of people's favorite bits are the electromagnetic spectrum, because it's the bit that is easiest to learn. So we've got a list of things. There's 7 of them. I think I've counted them right this time. So we've got radio waves. Radio waves have the longest wavelength. Microwaves are slightly shorter. Infrared, slightly shorter. So they're becoming shorter all the time until we get to gamma down here at the bottom. Gamma has the shortest wavelength. Longest, shortest. We can talk about them another way around, though. So we can turn it over. So radio waves have the lowest frequency. It means they come least often. Gamma has the highest frequency, meaning that they are most, they come together. So if we were to draw those waves, we'd have a radio wave, might look a bit like that. A gamma wave will look a bit like that, right? So much closer together. And we can put something else on here as well. So these three down here, you see how I've grabbed them together and I've written ionizing next to them. So radio waves have the lowest energy. Gamma has the highest energy. And as we move down, obviously it increases, it goes with. So once we've passed visible light, once we're past the stuff that your eyes can see, we enter something called ionizing radiation territory. And there's enough energy in the ultraviolet light to damage, no, I won't say that, enough energy to knock electrons off the molecules, off the atoms in your body. And that means ions can form. You might be talking about ions tomorrow in your chemistry exam. But when ions form in a biological sense, so in bodies or plants or things, they can cause changes to DNA, they can cause mutations, and we can end up with the cancer thing. Okay, so ultraviolet, X-rays, and gamma rays are all ionizing radiation. Too much ionizing radiation can lead to cancer. Okay, so watch out for that. They do like to ask that. They sometimes will wrap that question up with something to do with radio waves. So they might say, why is no one bothered about being exposed to radio waves? And it's because the waves are so low energy. There's not enough enough there to do any damage to your body, really. Yeah, most of us have had an X-ray, and if you're thinking, you might start panicking because you went for an X-ray at the dentist the other day. X-rays are brilliant, actually, because they travel through the soft stuff. So they travel through your skin, they travel through your muscles, but they don't travel through the bone. Okay, so the tough stuff in your body doesn't allow X-rays through, and that means that don't know why I'm pointing at gamma. That means that the X-rays will leave behind a pattern that shows the bones in your body. So we can use X-rays to look for broken bones. We can look at bone tissue density and stuff like that. It's some interesting science and some medical science that we can do with X-rays. Gamma rays. Gamma rays are a bit of a funny one. They are nuclear as well as electromagnetic. These are all electromagnetic. These gamma rays can be used to treat cancers, actually. So can X-rays to a certain extent. Because the very same high energy property they have means that we can use them to kill cells. So we can very carefully target certain cells, cancerous cells or damaged cells that we want to kill off. And we can kill just those cells and leave the cells around them relatively unharmed. And if that means that we can shrink a brain tumor or something, then it's worth a go, right? So these three down here are dangerous because they're ionizing. Ionizing radiation can lead to cancer, but we can also use them very usefully. Ultraviolet can be used to sterilize things, so we can use it for killing bacteria on food. X-rays obviously used for medical imaging, so looking at broken bones. And gamma, yes, can cause cancer, but also an incredibly powerful treatment tool as well. Okay, so that's electromagnetic radiation. A couple of other things on those. They're transverse waves. Okay, so transverse is T-shape. So there's a right angle in the T, and that means that the oscillations, that's the best thing to say. Oscillations is a posh word for vibrations. It's basically the wiggly bit, the bit that goes up and down, right? They are, those oscillations are at 90 degrees to the direction of the travel of the wave. So if a wave was moving left to right across the room, transverse wave, the particles would be moving side to side, a bit like wiggling a snake, okay, as the wave progresses. The other sort of wave, like sound waves and some earthquake waves, they are longitudinal waves, and that means that the oscillations are moving forward and backwards along the wave. So if the wave is coming towards you through the screen, the particles are moving forward and backwards right now. So then they're wiggling backwards and forwards in the air towards the microphone, okay? So the energy and the oscillation are in the same direction. Transverse, longitudinal. Okay, so try and remember that. They love asking that question. It comes up 1 or 2 marks almost every year because students get a little bit wrapped up in it, so it's worth knowing. Okay. All electromagnetic radiation travels at the same speed in a vacuum, but they're not going to they're probably not going to get too technical on that one. But you do get slight changes in speed for the different things as they pass through different materials. If they ask you though, light always travels, light, infrared, microwaves, all of them always travel at the same speed in a vacuum. Okay. That's probably about it for light. We can tie in with that a little bit about satellite communication. So we can put satellites in orbit above the Earth. Is that the traffic analogy you used in a lesson? It might have been. It's more likely I was talking about current when we were talking about traffic, where current can divide and go down 2 ways. Can you go over refraction? Yes, I can do refraction in a moment for you. There's an equation that goes with this lot as well. So speed equals wavelength times frequency. Again, this is on page 2 of your exam booklet. And just pull data out and use that from within. Now, Marin's asking about refraction. So if I hey, I watched a guy write live on YouTube. Okay, so if we take like a glass, right? This is the best example. So air and glass. If I shine light, a beam of light into glass, it refracts. So that's what refraction is there. Was my one car breaking, I think? Yeah, Aaron, I think I was talking about current with that one. I'll do you something on how current behaves in circuits for you if you like on Thursday. Okay, we'll go back to that. So on this one, with this refraction idea, as the light comes in, it's forced to slow down because light travels slower in glass than it does in air. So it goes slower. And as it goes slower, it's forced to bend slightly because a bit like if you're driving a car along or walking and one of your foot like stands in the mud, you kind of get like spun round because you've been slowed down just on one side. So the light is slowed down differently on the 2 sides. And that causes it to bend towards this little line here. It causes it to bend towards the normal line, so this little line here. If I redrew the diagram, but this time with the light coming out, so if it was coming out of the glass and into the air, this time it would be speeding up. As it speeds up, it would bend away from the normal, okay? So you have the 2 cases and they work, if you pardon the expression, mirror image to each other. Reflection is like refraction, except there you just have the bounce straight back off the surface, okay? Some of the triple awarders need to know about total internal refraction. That's where light is trying to escape and ends up bending back. Yes, the normal, Marin, is that line there. That little line doesn't really exist. It's an imaginary line that we've drawn at 90 degrees to the boundary so that I can measure that angle there, which I would call I for incidence, or the thing that happens. And that one there would be R for refraction, okay? And this one, that one's the normal one, okay? So this one here that we pointed out here. This is really difficult to do in the mirror, by the way, everybody. Okay, so there you go. So that's refraction. Has that helped you with that bit? Interesting uses for refraction, just while we're here. If anyone's got any questions, we can use, brilliant. We can use refraction for fiber optics. So the super fast broadbands, pinhole cameras, not pinhole, keyhole surgery using fiber optic cameras, endoscopes, that sort of stuff all relies on total internal reflection, but refraction. And that means that we can do surgeries quicker, we get faster broadband, things like that. We can communicate data a little bit quicker. And that's all to do with this slowing down of light as it tries, speeding up of light as it tries to leave. Okay, so all very clever and, if I'm honest, very useful physics, I think. I'm just going to check if I've got anything left on my pad. That's it. That takes us to 29 minutes and 40 seconds. So I will, on Thursday evening, I will do seismic waves for the triple award guys. I'll do a little bit on thermal physics for them. If you've got any questions in particular that you'd like me to look at, I'll do another recap on circuits. I've got a couple of tutorial videos now on circuits that you can watch. I'll do another recap there, though. I'll do a little bit more on domestic electricity. Got another couple of tutorial questions on those as well, though. And just make sure that everything's there. I'll do, yes, I is the angle of incidence. I'll also try and do something on conduction, convection, and radiation, because that's something I've left alone for tonight. I think we've done enough stuff already. So those are the things I'm going to go through on Thursday. If there's anything extra, feel free to stick a little question or a suggestion for what you'd like me to go through in the comments. Share and tell all of your friends, obviously. That'd be lovely to see if we can get lots of people involved for Thursday evenings. About 8 o'clock again. Okay, thank you very much. And I'll see some of you on Thursday, and I'll see some of you hopefully Thursday evening. Thank you very much.